hours are mandatory. So a lot of you guys are missing them and you're losing points every week, and you don't want to lose those points, especially when you get down to the end and you're kind of borderline. You want to have those office hour participation points. So not just showing up, but showing up and participating. If you just show up, then you only get 1 point. If you show up and participate, you get 2. So you remember that you need to show up and participate during office hours every week. I know that you guys always are telling me how hard this class is, which it is a hard class, but then you show up to office hours and you're like, no questions. That can't be true. How could that possibly be true? That you guys are in this super difficult class, but you have no questions. So make sure you are doing the work to come up with the questions that you have, because you don't want these questions to just show up when you're doing your exam, right? You want these questions to come up early in office hours so that I can help you to clarify a few things. So if you're not putting in work, you're not actually formulating questions, and that's going to be your issue. So make sure that you are taking advantage of the time that I'm giving you every single week to help, because our exam is coming up pretty fast. I think it's next week. So that means your learning assessments and your exam will be next week, I believe. But look at the syllabus for the exact date of everything. Because remember, I don't change the dates. I might change the content, but I don't change the dates of the exams. Anyway, all right, let's begin with prayer, and then we'll jump back into our polymerizations. Dear God, thank you for this day, and I thank you for these students. I thank you for the minds that you've given them for science, and how you have chosen them before creation to change the world, Lord. So I thank you for your plans for their life. I thank you that you have your hand on them and that you want to work out your purposes in each and every one of them. I pray that we would submit to your will, to your ways, so that we could glorify you, Lord. I pray that this week you would bless us in everything that we are discussing. Help us to help the students to learn, help me to teach it clearly, so that they can absorb the information. But I pray that you'd be in our midst, revealing to us more than just organic chemistry, but revealing your character, Lord, revealing your heart for us. I pray that you would bless them with health, with healing in their bodies. I pray that you'll bless their family members and the other things that they have going on, Lord. You know the prayers that each student has. I pray that you would be with them in those things. We pray this in Jesus' name. Amen. All right, so we are talking about our polymers. We know the polymers are these plastics that we have all around. So one of them, a very popular one that you know of, is polyvinyl chloride, or PVC. So this is made through a radical process. So we just talked about that radical mechanism. So using chloroethene or vinyl chloride, you put a bunch of these vinyl chlorides together, and so you get polyvinyl chloride. So with the reaction, it is regioselective. So every time, so if we have this, so remember we have an open bond, meaning this is extending to the left. So we have a CH2 bonded to a CH with a chlorine. Another CH2 bonded to a CH with a chlorine. CH2, CH with a chlorine, etc. We keep extending that, but at the end of that long chain, we end up with a CH with a chlorine where we have an unpaired electron. Every time we add another one of these alkenes, we always are going to add the CH2 to the carbon that has the radical. The carbon that has the radical is always going to be this carbon with this chlorine on it, because that is more stable. It's relatively more stable to put the unpaired electron on the carbon with the chlorine than it is on the carbon with 2 hydrogens. So this is regioselective. The reaction's only going to happen in a certain region. We don't get this kind of thing where we get CH2 and then CHCl and then another CHCl and then another CH2. We don't get this. This doesn't happen because this is a regioselective reaction, so we only get this CH2, CHCl, CH2, CHCl. It has a regular head-to-tail structure, a regular head-to-tail structure. So this is PVC. PVC is actually really hard. It's a very firm substance, but you know PVC is in things like garden hose or vinyl leather, plastic covers. So how does it become more movable, more elastic? Well, they add these esters that are called plasticizers to the whole mix of the structure. So there's PVC, and then there are these esters added in. Remember what an ester is? We have our carbonyl, oxygen, and then some R group. That's what an ester is, and so that gets added in to PVC. So that's our radical polymerizations. Now we have anionic. So we talked about acid catalyzed, we talked about radical, and now we're talking about anionic. So we can use one of our strong bases, so alkyl lithiums, so R, Li, the amide. So an amide is this, like LDA, where we have a nitrogen with 2 lone pairs and 2 bonds and a negative charge. We remember that this has a partial negative, lithium has a partial positive, and alkoxide is oxygen with a negative charge, and then you know what hydroxide is. Any of those can be used to initiate this anionic polymerization. So here's an example on the bottom. So we have hydroxide, and you only need a little bit of it. You just need trace amounts. We can even put that we need catalytic. Just a little bit around, that will allow for the polymerization to begin. It will initiate this polymerization. So once this thing with a negative charge reacts, we have to end up with something with a negative charge, right? We have an overall negative charge. We have to end up with an overall negative charge. So once we react, we move electrons onto this central carbon. So I'm going to call this R. And so this is really just the chain can extend as much as it wants in either direction, to the left, but I'm going to have R, and then I have that carbon that is bonded to these 2 groups. And so here it has a lone pair. I'm going to put the negative charge on that carbon. And so this structure is stabilized by resonance. So you should be able to see how it is stabilized by resonance, but I'll draw this. So we draw our arrow from the lone pair into the middle of the bond, from the middle of that bond up to oxygen. So we end up with a double bond, and now our oxygen has the negative charge. And so we have our oxygen with a negative charge. I can draw another resonance form where I move the electrons back into that bond, and I pivot these electrons. So middle of this bond into the middle of this bond, and then from the middle of that triple bond over to the nitrogen, because we have a partial positive, nitrogen is pulling electron density away. Same thing over here, partial negative, partial positive on that carbon. So electrons are being pulled toward the oxygen, so we can put negative charge on the oxygen. Electrons are being pulled toward the nitrogen, so I can draw this resonance form, where now I have a double bond between these 2 carbons, a double bond between carbon and nitrogen has 2 lone pairs on it, and so it has a negative charge. So what have we done? We can delocalize that negative charge, right? It's on carbon, it's on oxygen, it's on nitrogen. This is stable. It's stable for us to attack the carbon that's in blue right here. This blue carbon, we attack that with our strong base, and we move electrons onto this carbon that's in between these 2 electron withdrawing groups. With these 2 electron withdrawing groups, we can delocalize our negative charge, which stabilizes this intermediate. So this intermediate is stabilized by resonance. And so then we use that lone pair to attack the carbon of the next monomer unit. And so when we attack that again, we put that negative charge onto this carbon where this is still stabilized by resonance. So every time we add, we're always going to put this lone pair and negative charge onto this carbon between these 2 groups where we can delocalize that negative charge, which stabilizes that intermediate. If we put the negative charge on the CH2, we can't stabilize it. We can't delocalize it at all. So the negative charge knows it wants to be on that carbon with the ester and the cyano group on it instead. So this is actually the monomer. This compound is what's present in a container of superglue. It's just this container, a whole bunch of this container sitting there. It doesn't react until it's in the presence of some kind of hydroxide that will help it to begin this reaction. Where do we get this hydroxide from? Well, remember that there's water in the air, right? There's water in the air, and water exists as hydronium and hydroxide. So that little bit of hydroxide that exists from water, so remember this. I should put the negative charge there. Remember this, we have the positive charge, we have a negative charge, hydronium and hydroxide. Where does this hydroxide come in? Well, it's going to initiate this reaction. So this helps this polymer to form very quickly with just a little bit of hydroxide around from the air. If you get superglue on your hands, what's on your hands? You have a little bit of water on your hands, right? That little bit of water on your hands allows for that polymer to form, and the superglue holds your two fingers together because it's forming between your fingers. So you know this is a really tough substance that can't really be broken apart once it gets formed. We get this long chain alkane here that gets initiated with the hydroxide. Questions there? All right, then we move on. We're skipping 12-16 and we're moving on to 12-17 here. So for our natural products, remember what natural products are? These are things that exist in nature, in trees, in plants, and animals, just natural products, things that are around, they grow naturally, they exist naturally. Many of these natural products contain pi bond. And so a lot of them have this alkene in them. So specifically what we're talking about here are insect pheromones. So remember what pheromones are. They're the chemicals that these insects or any species can release to communicate to one another. And so they're communicating messages about sex, alarm, trail, defense, and more. But these get released so that they can send a message from, from one insect to another is what we're talking about. But animals and we have pheromones, etc. But anyway, so when we look at at insects, one of the things that they study are the different pheromones that they will release. So if you discover a new natural product, one of these new pheromones that the insects release, you isolate it, you characterize it, figure out the full structure of it, figure out all the stereochemistry in it. Then a synthetic organic chemist takes that structure and designs a total synthesis. And so remember, a total synthesis is where we start off with simple commercially available things and we build up to that product. The insects are only releasing like really super small quantities, like nanogram quantities or even less of these substances. And so sometimes you have to even kill the insects to get the substance, to get a larger quantity, but it's still a small quantity. So you want to really make the compound outside of the insect where you don't have to have the insect around necessarily, but then you can do the biochemical studies once you have synthesized the compound that they're making naturally, but you're synthesizing it in the lab. So here are some different alkene containing pheromones. Stereochemistry is important. So you see here we have cis double bond, trans double bond for this European vine moth. Male boll weevil has this four-membered ring in there. American cockroach has these oxycyclopropanes, which you see we also have these alkenes present. I want to point your attention to this one though, bombicol. So with bombicol, this is released by the silkworm moth. And so with this compound, look, it's a very simple compound, a bunch of carbons, two double bonds, and then an OH. But this compound specifically has to be where you see a trans here and then a cis here. So 10 trans, 12 cis. 10 trans, 12 cis. If you changed it to where this was cis instead and this was trans, if you changed it, if you switched it up, then that would be 10 billion times less active. if you switched it from what you see, which is obviously trans and cis, if you switched it to cis here and trans here, then that would be 10 billion times less active. If you change them both to trans, if they were both trans, that would be 10 trillion times less active. 10 trillion times less active. The molecule has to be where we have this trans double bond and this cis double bond in the right place. That's the only way that this silkworm moth can pick up this compound. Because of the receptor, it knows this source is trans. If you try to change the stereochemistry at those double bonds, it doesn't work. So why do we want to do this? Why do we care about these pheromones? Well, if you isolate these pheromones and you study them, this can open the door to new pest control methods, safer pest control methods. So what we can do is make this insect lure, this trap here. And so with this, if you coat it with pheromones of whatever insect you're trying to lure in, it will bring them in, lure them in, and you can contain them in a certain place without having to spread out, to spray like crops with insecticides, without having to do all this that can be detrimental to human health or to the environment, putting all these different chemicals, out onto these crops or trees or whatever. Instead, we can make these lures. And so here's a pheromone trap for the males of the pea moth. So if it lures in the males of the pea moth, then obviously there's no males there to reproduce with the females, and so the population declines. So it lures in the males thinking that they're finding a female. They're not. They are just being pulled out of circulation, and so then they can reduce the reproduction of these insects that are going to eat the plants and destroy different things. So pretty cool stuff that is being done with pheromone research. Any questions on that? All right, so again, we're to the end of a chapter where we look at the alkene reactions. What are the reactions that we can do? Well, we learned in this chapter some different things like hydrogenation, HX, hydrogen, proton and water for this reaction. We also saw these reactions with H2SO4, where we can turn cis into trans, or where we can turn a terminal alkene into an internal alkene. There are things that we didn't learn, though. Like this is chapter 12. I did not do this reaction with you. These reactions exist, and you can definitely read about them, but you're only responsible for the ones that we actually went over in our class. So here we get back to like MCPBA, our osmium tetroxide. So look at the reactions here, take it with a grain of salt, but also remember that in the back of the chapter, kind of beside this page, there's another page where it kind of lists them out, and it gives you very general formula for the different reactions, and so you might want to write that down. All right, let's get into our learning checks. Hopefully you did these ahead of time so that you can look at your answer rather than having to copy down every single thing that I'm writing. You can just check your answer. All right, so we have an alkene, we have hydrogen and rainy nickel. Rainy nickel can also be written like this, RANI. But what is this reaction? Hydrogenation. And so here, as we do this reaction, we're starting off with this alkene. When we do this reaction, any kind of a catalyst, the palladium 1 carbon, rainy nickel, platinum oxide, platinum 2 oxide, we're going to end up with just the alkane. Alkene turns into alkane. Another way to draw that would be like this, where we have our 5 carbons on the horizontal a bit more. This is kind of skewed at the top, and if you turn it slightly, then you have it more on the horizontal. But that's all we're doing there. So we're ending up with this carbon that now has 2 hydrogens on it and a CH3 with a single bond to a carbon that has this methyl. It's added in a hydrogen and this CH2, CH3. So we're gaining hydrogen and hydrogen from H2. That's all that's happening in this reaction. Questions on this?
Yeah, I have a quick question. If you have an excess, will all of the double bonds turn
Yes.
into alkanes? There's
Yes.
no circumstance where any of them won't?
No, there is. So that's called partial hydrogenation, and so that's something that they do in the lab where you are turning some of the double bonds, but you're not turning all of them. But no, I will either give you just one alkene, and so one equivalent of hydrogen, or an excess with numerous alkenes. But it does exist in real life.
Professor, I had a question regarding the formatting of it. So, do we do the molecular formula or the structural formula?
You need to, it's better if you draw it in this way, just because this is quicker, right? If you do this and I see a CH2 here instead of a CH3, then I mark the whole thing wrong. So it's better if you don't, but I'm just showing you this so that you can see, we had one hydrogen here. I'll do it like this. We had one hydrogen here. That hydrogen is still there, but now we've gained two more hydrogens. So
And I'm
each
more
carbon,
comfortable doing the line instead of the molecular because molecular just makes it very confusing for me.
molecular formula, this isn't molecular, this is called
No,
condensed.
no, I know. But like, when they write out the methyl CH3 and stuff, I just it messes with my head. It's better for me
Yeah,
to
so I would say draw it out, like you're talking about in the
yeah,
solutions manual. Yeah,
yeah.
draw it out. All right, so the same exact starting material. And with this, we're adding in chlorine and methanol, right? MEOH is another way we could write this. And so what's happening in this reaction? Well, we have our chlorine, and with the chlorine, we can polarize this bond, and we make one of our chlorines the electrophile. So from the middle of the bond to the chlorine, from the middle of the bond to the other chlorine that's pulling electron density, and then from the lone pair to one of these carbons. You need all three of those arrows. Now, the mechanism was not requested here, but I would say it's good to do the mechanism because it's really hard to figure out stereochemistry of your product without it. All right, so when we do this, the chlorine still has two lone pairs on it. It has a full positive charge, and we need to show the stereochemistry that we had in our starting material. So the two methyls were on the same face to one another, and so I can either do both methyls as a wedge, which I'm going to do, or both as a dash. And so if that is on a wedge, then what's on a dash? Well, here I have this ethyl, and over on the other side I have a hydrogen. You know that the hydrogen is there. I'll number this 1, 2, 3, 4, 5. You know that there's a hydrogen on carbon 2. So with this, I said I could do it with the two methyls as a wedge, or I can do them as a dash. So this is really racemic. This is racemic. All right, so what is going to react? I have two things around, right? I have chloride. I have a little bit of that, but I have also methanol. Which one is going to react? Well, it doesn't matter that chloride is a better nucleophile. Even though we have a poor nucleophile here, we have it in excess. Because we have it in excess, that's what's going to react. Here we have a positively charged chloronium ion. This three-membered ring has a positive charge in it. So we are going to attack the more hindered carbon. So from the lone pair to carbon 3. So we have our chloronium ion. We're going to attack the more hindered carbon. If I attack carbon 3, look at it. It has a full octet. So something has to give. I'm going to break this bond. Why am I breaking that bond? Well, it does have a partial negative. Even though it has a full positive charge, that chlorine bonded to carbon is pulling away electron density. And so we can break that bond. And as we break that bond, we get chlorine still bonded to carbon 2. The chlorine is still bonded to carbon 2, right? We didn't do anything to that carbon 2 chlorine bond. And so what else is on carbon 2? It still has carbon 1, and we leave it down there. But as we are doing this attack, this is an SN2 attack. So what do we get? Inversion of configuration, backside attack, inversion of configuration. Our leaving group is leaving. And so this methyl and the ethyl get pushed up, right? Inversion of configuration. We have to show this stereochemistry. Otherwise, we're not going to get the right answer for the product. So we get this oxygen. What does the oxygen have on it? Well, it has a hydrogen and a methyl. Those two do not magically go away. You have to have them there in your mechanism. And so this oxygen ends up with a positive charge because you know it has a positive charge when it has 3 bonds. So then the last step, we can just write minus H plus, but we need to have an arrow from the middle of this bond to the oxygen because, again, this has a partial negative. This has a partial positive. Electrons are being pulled toward the oxygen. And so we end up with this as our product. A methoxy group added from the methanol. So our methoxy group added, this is our product. We've shown stereochemistry. We said this was racemic. This is also racemic. This is also racemic. But we want to draw this in a different way. We want to draw our carbons 1 through 5 here within the molecular plane on the horizontal. We want to put them into the plane, those 5 carbons, and then we want to have the chlorine on carbon 2 either coming out toward us or going away. We want to have on carbon 3, we have a methyl and a methoxy. We have to figure out what the stereochemistry is there as well. So again, if you can't see this, that's an issue. You need to be able to rotate this first structure in order to get things into this structure here. So basically we have 1, 2 coming toward us. We want to push it back slightly. As we push back on 1, 2, hydrogen pops up, chlorine comes toward us, and so chlorine we could write here as a wedge because we know hydrogen is on the dash. So at the top, they're both at the top. So we had 2 things at the bottom. As we have 2 things at the bottom, we push 1 thing at the bottom into the plane. Then we get 2 things at the top now. So hydrogen was in the back here, but down. Now it's in the back at the top. All right, then we move on to carbon 3. So we have our carbon 4, 5 in the back. We want to pull it forward slightly. It's in the back. We want to pull it forward slightly. As we pull it forward, then this methyl goes down, but it's still in the front. And the methoxy gets pushed to the back. So our methoxy is in the back, and our methyl is in the front. Same product. I just redrew it, just with a different conformation. But this is how we want to get to our final answer. We want to show the stereochemistry. We want to show the connectivity in our product, but also we want to say, okay, this is racemic. So in this reaction, what did we get? We can see that this is an anti-addition, right? Anti-addition, chlorine gets added at the top, and the oxygen got added at the bottom, anti to one another. This is also Markovnikov addition. We said H or the electrophile. What was our electrophile? Our electrophile is the chlorine. H or the electrophile gets added where there are more H's. Where were there H's in the beginning? On carbon 2. Carbon 2 had more hydrogens than carbon 3, and so carbon 2 got chlorine in the end, whereas carbon 3 got the nucleophile. So Markovnikov and anti-addition here in this reaction. Questions on this?
Doctor, I have a question. So, are these the ones where you said that you could also just write racemic and then, like, or we don't have to show both. We just have to show that. We just
Well,
have
I
to
haven't drawn the other one yet, right? I didn't draw the other one. The other one is this. This is the other enantiomer. I didn't draw it. I just wrote racemic.
Okay, thank you.
So if you had gotten this and written racemic underneath it, that's fine. Or if you got this and wrote racemic underneath it, that's fine. Or you can draw both products. Other questions?
Okay, so for that first racemic mixture, when we first added that one chlorine, can you explain how it became a cycloalkane right there?
Because of the arrows in the beginning? Because of the
Yeah.
arrows right here?
Yes.
It's because of the arrows. So from the middle of the bond, they attack the electrophilic chlorine, and then obviously the chlorine bond has to break, but then the other chlorine brings in electrons to make the chloronium ion.
Mm.
So this is from the note. So go back. I'm not telling you, when I get to learning checks, I'm not teaching you anything new. I'm just reiterating things I already told you in the chapter. So make sure you have, gone over what's in the chapter. But yeah, we talked about this when I introduced, so we had the bromonium ion and the chloronium ion. So with chlorine or bromine in the beginning, we said we're going to do 3 arrows to get this 3-membered ring. Rather than having a sextet, we have full octet. So go back and review that part.
Okay, thank you.
Uh-huh. All right, let's move on to this last one here. On these 3 were all on the same slide. All right, so what's happening here? We have HBr. We cannot just keep HBr written like that, right? We need to show the bond if we're going to do a mechanism. If we're going to do a mechanism, we have to explicitly show all of the bonds, and it's really good if we add in the partial charges. So from the middle of the bond to this hydrogen, from the middle of the bond to bromine. So what's happening here? Well, we have a base, and we have something that is acidic. So where is the H going to go? This is the Markovnikov addition. Carbon 1, 2, 3, 4, 5. What we know here, looking at this, it's going to go either to carbon 2 or carbon 3. Carbon 2 has 1 hydrogen on it. Carbon 3 has no hydrogens on it. And so H goes where goes where there are more H's. And so I'm going to end up with this carbocation. So what do I know about carbon 3? I know carbon 3 is trigonal planar, right? Carbon 4 isn't trigonal planar, it's tetrahedral because it has 4 bonds to it, so it's tetrahedral. But carbon 3 with a positive charge, that's trigonal planar, which means I have this bromide that is going to react at that carbon, so from the lone pair to that carbon. And so it can attack from the front or the back, or we can say top or bottom. Because this is trigonal planar, bromide can come in from the top or the bottom, from the front or the back, however you want to visualize it. So that means I get this product where the bromide came in from the front, and I get this product where the bromide came in from the back. What's the relationship between these two? Are they enantiomers, diastereomers? Same? Put it into the chat, please. E for enantiomer, D for diastereomer, S for same or identical. What do you think? What's the relationship between these two? Put that in the chat, please. So if they were diastereomers, there'd have to be something that doesn't change. Look, it's changing. Bromine's on the wedge, and then it's on the dash. Are these enantiomers, though? Do we have 4 different things on this carbon? Is carbon 3 a chiral carbon? No, it has 2 ethyls on it. They are identical. Yes, these 2 are identical. So really what's happening is this is achiral. This is an achiral carbon. And so if it is an achiral carbon, really our product is this. Because it's achiral, we don't have to show any stereochemistry, we just draw the product like this. But if there was a difference, so if we started off with if we got this kind of a product, then you know this product is chiral, right? This is a chiral carbon now. So then we would have to show both enantiomers, or we'd have to draw one and write racemic underneath it. Or if we had diastereomers, we'd have to draw both diastereomers and write unequal. You have to pay attention to what's happening in the course of the reaction. So yes, even though bromine can attack from the front or the back, as we do this reaction, we have 2 of the exact same groups attached. We have an ethyl and an ethyl. We need to have 4 different groups in order for it to be chiral. All right, questions on that?
Yes, Professor. So can we call them meso in one anyway?
This isn't a meso compound. A meso compound has to have a chiral carbon.
Has to have a, oh yeah, right, chiral
Well,
carbon.
it has to have 2 chiral carbons.
So and
This doesn't even have a chiral carbon at all. So this
when
can't be
there's
meso.
when there's meso, we only have to write 1 compound versus when we have race mates, we write 2, right?
Yeah, well, you can just write racemic underneath it if it's racemic.
Okay, I'll just write. Okay, and for the where we have achiral like this, we
Yeah.
have the same molecule. Do we have to show the other one too?
No, because there is no other molecule. Because it's achiral.
The same thing.
Yep.
Okay.
All right, let's do this one. So what do we have over the arrow? H2SO4, a strong acid, which we can represent as H+. If you're going to do this, you cannot just do this. This isn't correct. You can't try to do a mechanism and just say, oh, no, that's not how the structure looks. You cannot do that. So it's easier if you just write H+ to represent acid, or if you're going to do it, you have to draw the whole molecule for H2SO4. So what do we have? Acid, and we have a base. So acid-base reaction, we're going to go attack that proton. And so as we do this reaction, remember, this stereochemistry for this methyl needs to stay, right? This is a chiral carbon. It's tetrahedral. We can't lose that stereochemistry unless the reaction is happening there. All right, so this is a Markovnikov addition. So which carbon gets the hydrogen? Well, if this is 1 and this is 2, then carbon 2 would get the hydrogen. Carbon 1 gets the positive charge, right? Because we get a tertiary carbocation. So you can always tell, where's the carbocation going to go? It's going to go to the carbon that's more substituted, because H goes where there are more H's. All right, so remember that this is a non-nucleophilic strong acid. And so we don't have a nucleophile around unless we use water. Even though it's a poor nucleophile, it is still a nucleophile. So we have our water molecule. Now, what do we know about this carbon here, though? We know that if it has a positive charge, it's trigonal planar. So if it's planar, the oxygen can attack from the front or the back, or we could say top or bottom. So here, I'm just going to draw this arrow from the lone pair to the positive charge, but know that it's happening on both sides. And so as it's happening on both sides, I'm going to get these 2 products. keep the hydrogens that are attached to the oxygen, positive charge there, and I'm also going to get this product. Now, why am I drawing two products here? Why am I drawing two products? Are these two racemic? Are they formed in equal or unequal amounts? Can you put that in the chat? Equal or unequal amounts? Are they formed in equal or unequal amounts? Yeah, they're formed in unequal amounts. Exactly. So that's why I have to draw both of them. So even though these are intermediates, which one is the major intermediate? We'll call this one on the left A and then the one on the right B. Which one do you think is going to be major? A or B? Which one do you think is major? A or B? Yeah, this is the major. It's just an intermediate, so it's not our major product, but it is our major intermediate here. Why? Because the oxygen is attacking on the same face as the hydrogen that's over here. If I call this 1, 2, then 3, 4, 5, on carbon 5, there's a hydrogen. If there's something on a dash, something has to be on a wedge. And so we know that there's always a hydrogen on a wedge on carbon 5. So it's better for our oxygen to attack on the same face as that hydrogen than it is for it to attack on the same face as the methyl. So that makes this our major intermediate. So then what has to happen? We, from the middle of this bond to the oxygen, right? Partial negative, partial positive, middle of the bond to oxygen, minus H plus. We end up with this product. Now, again, nothing happens to that methyl that's on a dash over here on carbon 5. Nothing changes with that. The reaction isn't happening there. The reaction is happening between carbons 1 and 2. H goes where there are more H's. And so in this reaction, carbon 2 got the electrophile, it got the H, and then carbon 1 got the nucleophile. And so for these, which one is the major product now? A or B for the product? We talked about the intermediate, now product. Which one is the major product, A or B? Yeah, it's still A. If that was the major intermediate, then of course, this is going to be the major product. Nothing changed there. So for this, yes, you need to draw both because they are diastereomers. Because they are diastereomers, you have to draw both products and you have to label one as the major product. You have to show stereochemistry. Doing the mechanism helps you to think about how you are getting a trigonal planar intermediate, which means that the oxygen can attack from the front or the back. This isn't an SN2 reaction, right? We're not getting inversion of configuration. We're making a carbocation, and as we make a carbocation, we are attacking from both faces. Questions on this? All right, so here we have an alkene with catalytic acid. We said acid is H+. How do we react this? We did this before. This is our third time doing this today, right? From the middle of that bond to that proton. So this is, again, a Markovnikov addition. Every time you're doing this acid-base reaction, it is Markovnikov addition. H goes where there are more H's. So if I call this 1, 2, 3, 4, then where does the hydrogen go? Give me a number. 1, 2, 3, or 4 in the chat, please. Where does the hydrogen go? Yeah, it goes to carbon 1 because that has more hydrogens on it, right? It has 2 hydrogens on carbon 1, and then carbon 2 has 1 hydrogen. So H goes where there are more H's. So we end up with this as our carbocation. We know that a secondary carbocation is okay, but tertiary is even better. If I draw in this hydrogen from the middle of the bond to the carbon, I'm doing a hydride shift from the middle of the bond to the carbon. Again, I want you to note that if I drew this arrow from the middle of the bond into the middle of the bond, that would give me an alkene. That wouldn't give me a hydride shift. So now I've done a hydride shift to show my more stable carbocation. So now with this, remember we have a hydrogen here, call that A, hydrogen here, call that B. Which one is going to be more likely to react, A or B? Which one is going to give me a major product here if I react with A or B? What do you think? Put that in the chat, A or B. Which one is going to be more likely to react here? Yeah, B. And so with that, minus a proton from the middle of the bond into the middle of the bond, I end up with this as my product. So now I went from a double bond between 1 and 2 to a double bond between 2 and 3. So you might be wondering, okay, why didn't we just do that here? Well, because this isn't correct, because you're going from a secondary carbocation. If you can access the tertiary, it's going to access the tertiary in the mechanism and then get you to your product. But what are we doing here in this reaction? Well, we are changing a terminal alkene into an internal alkene. And we know for internal alkenes, they're going to be more stable. Right? We took a mono-substituted alkene and we turned it into a tri-substituted alkene. We know that that's going to be more stable. So we use a catalytic amount of acid and we heated it up, right? If we have heat, that is going to favor eliminations. Think back to what we talked about in chapter 9 and in this chapter. Adding and heating it up is going to favor elimination. So we protonate and then we deprotonate in this equilibration. So we talked about this equilibration, and we said that this is under kinetic control initially, where just all possible products are formed. And then as the reaction proceeds, it goes under thermodynamic control, where here, this product is more thermodynamically stable. And so the product that's more thermodynamically stable gets formed when it's under thermodynamic control as you let it go over time. So remember those slides. Questions on this?
Professor, quick question. So you said that this is Markovnikov, is that right? So like,
Addition, yeah.
so in Markovnikov, as far as I know, you go to the one that's most substituted. Is that right?
No. H goes where there are more H's. H or the electrophile goes where there are more H's, right?
Because the instruction manual, they told us over here, like it goes to the most substituted part. That's as I was.
What is it though? Is it the nucleophile or is it the electrophile? What is it? You know what I mean? So yes, when we were back here, let's see here. When we were here, we said that H goes where there are more H's. And so we added a hydrogen to carbon 2. Carbon 2 got the hydrogen, but carbon 3, which was more substituted, right? It's more substituted, that got the nucleophile.
Okay, so maybe they were talking about the nucleophile.
You have to pay attention to, yeah, that's what I'm saying. What is it? What specifically are you talking about? Because H or the electrophile goes where there are more H's so that we can end up with a carbocation that is stabilized.
Okay.
Other questions?
I have a question.
Yeah.
So could you clarify again why you can't attach the hydrogen to the middle of the bond instead of like
Which
the thing
one?
on the left that you showed with the
Why we can't do this?
Yeah.
So with this arrow is just showing making this double bond. That's what the arrow is showing. But this is incorrect because you're going from a secondary carbocation, which is not what we would have. Really, what we're going to form is a tertiary carbocation and then react there. And so for this, yeah, it's simple. But what if we have this kind of a thing where you have a positive charge here? If you're reacting with this, you're not going to get the right product because this is going to turn into this, which is going to only access certain products versus this one. So you, because there's only one, we're just going from a secondary to a tertiary. So you're going to end up with the same kind of product either way, but here you wouldn't end up with the same product. So from this, you could only end up with maybe this one or this one. Whereas here, from this product, from this intermediate, you can access this one. They're different products. And so I'm just reminding you that if you can form tertiary, you have to form tertiary because these rearrangement products can give you something different than what you would expect just looking at the starting material. That's all I was saying there.
Okay, that makes sense. Thank you.
Uh-huh. Other questions? All right, let's do one more. So here we have bromine. So I know I can draw this, right? Whenever I see Br2 or Cl2, I know I can begin to draw that. I know this one has a partial positive and this one has a partial negative. And I can just make whichever one I want. They're just polarizing. Electrons being pulled toward one of the bromines. But what is this? CCl4, what is that? That is our solvent. It does not react. It's inert, right? Unreactive solvent. Do not let me see some chlorines coming in here. No chlorine. CCl4, carbon tetrachloride, is just the solvent and it doesn't react. All right, so what do we do? Same arrows as before. Middle of the bond to bromine. We break the bromine-bromine bond, and then from the lone pair to the other carbon of bromine. The other carbon of the alkene. So as we do this reaction, we know we're going to get a bromonium ion, this three-membered ring, bromine with a positive charge. Because now this is a cyclic alkene, what did we say for cyclic alkenes? Cyclic alkenes, we're going to show the stereochemistry in these bonds to bromine. Cyclic alkenes, we show the bonds to bromine as either both wedge or both dash. Let me go back here. Let's see, another bromonium, or here we have a chloronium. Remember, this is an acyclic alkene. And so what did we do with the acyclic alkene? We showed the stereochemistry in the bonds here to the chloronium ion, and we kept these bonds in the plane. Those bonds are in the plane. But when you have your double bond in a ring, now you're going to show stereochemistry here, and you're going to keep the bigger ring in the plane. Because it's a bigger ring, we have now two rings fused together. Keep the bigger ring in the plane, and then have your bromonium either coming towards you or going away from you. So here we know that we get these two products. What is the relationship between these two products? So here, two wedges. What's the relationship between these two products? These are diastereomers. Exactly, perfect. If these are diastereomers, come on, then one of them is major. Which one's major? So we'll call it A and B. Which one's major, A or B? B is major. Why is B major? Well, here we have a small hydrogen on the same face as hydrogens, versus here we have the bromine, this large bromine coming in on the opposite face to where this ethyl is. It's coming in on the same face as this hydrogen that was there. This is going to be major because of steric hindrance. This large ethyl is taking up the top. And so bromine is going to come in from the back or bottom, the opposite face to where that ethyl is. So I'm just going to go forward with the major intermediate because there are some products that we're going to get here. So with this major intermediate, I'm just going to redraw it here. What do I have now to react with it? What's going to ring open? Well, I have my bromide. Where did this bromide come from? Came from here, right? From right there. As that left, we made bromide. And so I can attack this carbon, and these electrons go over here to bromine. Or I can attack, so just another bromide, right? We have a bunch of bromide around, so I'm just drawing this second scenario where we attack here, and the electrons go up here. So we'll call this B, and we'll call this A. So over here in blue, we'll call that A, where we're attacking that one carbon. Let me number this. So 1, 2, 3, 1, 2, 3. So we can either attack carbon 1 or we can attack carbon 2. So A is attacking carbon 1 and B is attacking carbon 2. We can do either of these things. Now, what is the regioselectivity of this reaction? Remember we said that the more hindered side is going to be attacked. Neither of these is more hindered. Carbon 1, carbon 2, same amount of hindrance. So both of these are possible. Both of these attacks, A and B, are equally possible for right now because of the steric hindrance at 1 and 2. There's no difference in the steric hindrance at carbon 1 and at carbon 2. So if I do A, then what am I going to get for my product? Bromine is going to still be attached. This black bromine is going to still be attached to carbon 2. But on carbon 1 now, I'm going to have a bromine that I've added from bromide. Notice that this is a wedge. Why is it a wedge? Because this is an anti-addition. So if the bromine that was already there is on a dash, then the other bromine comes in as a wedge. Now let's look at B. If we do B, then we're going to keep the bromine as a dash, but on carbon 1 now. Because we're attacking carbon 2, this red bromide got added to carbon 2, and again it gets added as a wedge, opposite to what we saw for the original bromine that got added there. These are the two products that we can get. From our major intermediate, we can get either of these two products. But with these two products, one of them is major and one of them is minor. Of these two products, these two are diastereomers of one another. Hopefully you can see that they are diastereomers. Yes, the major product is this one. Why is this a major product? Because we are attacking here far away from this large ethyl. We have to come in on the front, right? We have to come in on the same face as the ethyl. Because of where the bromine is, we have to come in on the same face as the ethyl with the bromide that's attacking. The nucleophile that's attacking has to come in on the same face as this bulky ethyl. What is better to do? It's better to come in on carbon 1 than for it to come in on carbon 2, where we get all this steric hindrance here where we have this large bromide trying to come in on the same side as a large ethyl that's already there. A lot of steric hindrance in that attack, but it's on carbon 1, now it's a bit further away, and so it's a bit easier for us to do that attack. So we get this as our major product, but we need to draw both. But again, that came from this major intermediate over here. So from this intermediate, this minor intermediate, we would also get 2 products there, but it's minor, and the products there are even more minor, right? A minor intermediate forms even fewer minor products. So we start with the major intermediate and get to the major products. All right, you guys, that's all we'll do for today. If you do have questions, you can stick around, but I will see you guys on Wednesday for lab, for lecture, Thursday lab. But have a good day, and I'll see you guys for office hours as well. Love you guys. Have a good day. Bye. You're welcome. Bye.
Dr. Navanian, quick
Thank
Yeah.
you.
So,
You're welcome.
how will we distinguish